Swayam Prabha. Digital India. Educated India.
Hello viewers, welcome to lesson 13 of module 4. Module 4, as you know, is on payment design. In this lesson, we will be discussing about designing flexible payments as per Indian Roads Congress method. The specific instructional objectives of this lesson will be, after completing this lesson, it is expected that the student understands the basis for Indian Roads Congress method for design of flexible payments. It is also expected that student would be able to select appropriate traffic and material inputs required for designing flexible payments as per Indian Roads Congress method. Also, he would be able to understand how to design flexible payments, how to select layer thicknesses, a particular specific design combination for a given situation as per Indian Roads Congress practice. It is also expected that at the end of this lesson, the student would be also be in a position to appreciate the limitations of the Indian Roads Congress method. As you see here, Indian Roads Congress guidelines for design of flexible payments are given in IRC 37. This is the number of the guidelines that is given by Indian Roads Congress. 2001 indicates the year in which the latest revision has been given. So, we are going to discuss about the provisions of Indian Roads Congress 37 2001. These guidelines are result of research work carried out by various institutions in India on the basis of performance data that is collected on different payment sections in India, and this version of IRC guideline 37 for designing flexible payments is considered to be more rational compared to its previous version, which was issued in 1984. The scope of these guidelines, that is IRC 37 2001, these guidelines are applicable for new payments. Theoretically, we cannot evaluate existing payments and try to design overlays for those payments using this IRC 37 guidelines. Also, these guidelines are applicable for design of flexible payments for relatively high volume roads such as expressways, national highways, state highways, MDR, ODR and other categories of road having a relatively high volume roads. What we are trying to indicate here is these volumes are not meant for designing low volume roads such as village roads. Also, these are obviously meant for flexible payments, typically having bituminous surfacing with granular base and granular subbase. The design criteria that is considered in IRC 37 2001 are basically, there are three criteria that have been considered to be important. This is rutting failure due to the permanent deformation that occurs in subgrade, that is the bottommost layer of the foundation. So, the subgrade can undergo permanent deformation that can result in the form of rutting, which can be seen on the surface. Second form of distress or failure that is considered is permanent deformation occurring in thick bituminous layers. Bituminous layers also can undergo permanent deformation when they are subjected to heavy loads at high temperatures. That also can result in rutting that can be seen at the surface. The other form of distress, the third form of distress that is considered in IRC guidelines is the cracking of bituminous layers, indicated as fatty cracking of bituminous layers. So, these are the three main considerations that are there in IRC 37, but only two of these considerations have been taken into effect for providing design criteria for designing flexible pavements. So, as you see here, these are the three main criteria: rutting due to permanent deformation in subgrade, rutting due to permanent deformation bituminous layer, fatigue cracking in bituminous layer. This sketch here illustrates the rutting that is occurring because of permanent deformation in the subgrade layer. So, this amount of rutting or permanent deformation that is occurring in the subgrade layer is getting reflected in all the subsequent layers and obviously on the surface. So, the difference in these two levels can be measured at the surface as rut depth. Rut depth may be occurring in any of these layers starting from subgrade, granular base or bituminous layers, but we normally consider two types of rutting that is occurring. One because of permanent deformation occurring in subgrade, that is what is depicted in this sketch. The next sketch shows the permanent deformation or rutting that is occurring at the bituminous surface because of permanent deformation occurring in bituminous layers itself. As you see here, no permanent deformation is indicated either in subgrade or in granular layer, but there is permanent deformation seen in bituminous layers. So, that is what is reflected as a rut depth on the pavement surface. This is another type of failure that is normally seen in bound layers. Since we consider bituminous bound layers, bituminous mixes to be bound layers, so they are susceptible to cracking because of repeated application of wheel loads. So, we see in this case cracking of this form, which is in chicken net or crocodile shape, rather the back of the crocodile. So, this is the shape, this is called as crocodile cracking. So, this is a very common mode of failure that occurs in bituminous layers. So, these are the three main forms of failures that are considered: rutting occurring because of permanent deformation in subgrade, rutting occurring because of permanent deformation in thick bituminous layers, and fatigue cracking occurring in bound bituminous layers. However, IRC 37 in its performance criteria considers only the rutting occurring because of permanent deformation in subgrade and fatigue cracking in bituminous layers. We have discussed about the general philosophy of pavement design in the very first class lesson 4.1. We also discussed about the analysis of flexible pavements, computation of stresses, strain, deflections in single layer systems, multi-layer systems. IRC 37 is a semi-mechanistic design approach in which the performance of pavements is explained in terms of the mechanistic behavior of different components of the pavement. So, the pavements are generally analyzed for determining critical parameters, mechanistic parameters, that is critical stress, critical strain, critical deflection, and these critical parameters are correlated to the performance of the pavement. How the pavement is likely to perform in resisting fatigue cracking, how the pavement is likely to perform in resisting permanent deformation in different layers. So, this can be explained in terms of the magnitudes of stresses or strains or deflections in a newly constructed pavement. So, typically these are the parameters that are considered. For a pavement loaded by wheel loads, the tensile strain at the bottom of the bituminous layer, as you see here epsilon t, is considered to be critical in explaining the fatigue behavior of bituminous layers. Similarly, the vertical strain on top of subgrade epsilon z is considered to be critical in explaining the permanent deformation behavior of the pavements. So, these are the two parameters that have been found to have good correlation to fatigue cracking of bituminous layers and also permanent deformation of bituminous pavements. So, one should be able to calculate for a given pavement system for a standard loading that is given these two parameters epsilon t at the bottom of bituminous layer and also vertical strain on top of subgrade within the subgrade. Then we can have some limits on these two parameters, so that the pavement is going to perform satisfactorily both in fatigue cracking and also in permanent deformation considerations. As we just indicated, these are the two main parameters that are considered to explain the performance of pavements. Vertical strain on top of subgrade epsilon z is considered to be causative factor for permanent deformation in subgrade. If these vertical strains are excessive, so one can expect that there is going to be excessive permanent deformation leading to the rutting which can be seen at the surface. Similarly, if there are excessive horizontal tensile stresses at the bottom of the bituminous bound layer, this is an indicator for fatigue cracking in bituminous layers. Flexible pavements should be designed to perform satisfactorily. For that matter, all structures have to be designed to perform satisfactorily without developing unacceptable levels of distresses during the design life period. We have used certain keywords here: satisfactory performance. They have to perform satisfactorily without the distresses being reaching unacceptable levels during the design life period. If the design life period of a pavement is say about 10 years, that is what we consider, let us say, then the pavement should not have excessive distresses during the design life period. What is to be done is, we have to define what is acceptable quantity of the distress. We have talked about two main forms of distress: fatigue cracking of bituminous layers and rutting in bituminous layers. So, if we measure fatigue cracking, that means measure the extent of cracking that is there on the pavement surface. What is acceptable during its design life period? 5%, 10%, 20%. Similarly, if you can measure the permanent deformation or rutting in bituminous layers, how much is an acceptable value? Once we have the definition, so we can accordingly design the pavements. We can see the definition of what is acceptable for the two main distresses that we consider, that is fatigue cracking in bituminous layer. Cracking in about 20% of pavement area is considered to be critical. That means, if the cracked area is more than about 20% of the paved area, that is considered to be not acceptable. Similarly, for rutting, an average rut depth of, for a stretch that we are considering, suppose if we are evaluating a 1 kilometer stretch, within that stretch if you measure rut depth periodically at different locations, then if you take the average of that, if that average happens to be more than 20 millimeters, this is a condition that is considered to be not acceptable. So, in the case of fatigue cracking, 20% of the area should not have cracking, rather the cracked area should not be more than 20%. Similarly, average rut depth should not be more than 20 millimeters. These are the conditions that we are trying to maintain during the service period of the pavement. To ensure that these unacceptable levels of distresses do not occur during design life period, unacceptable levels just defined, the critical mechanistic parameters identified as indices for performance, these you may recall are vertical strain on top of subgrade and horizontal tensile strain at the bottom of bituminous layer. So, these two parameters should be kept within acceptable limits. To ensure that the pavement do not have unacceptable levels of distresses, fatigue cracking and the rutting, we have to keep the identified critical mechanistic parameters to within acceptable limits. What will these acceptable limits will be different for different conditions, we will discuss about this subsequently. Just to repeat, For fatigue cracking, we have identified horizontal tensile strain at the bottom of bituminous bound layer epsilon t as a critical parameter. For rutting, vertical strain on top of subgrade epsilon z as a critical parameter. These two parameters, these two strain values can be computed using a suitable theory. So, we have to select a suitable theory to analyze pavements, then we calculate them, and then we can decide for a given pavement depending on the values of these two strains whether it is going to be an acceptable design solution or not. So, the design of a pavement, design is nothing but selecting layer thicknesses and also the layer materials and also the type of pavement, what combination of materials we are going to use, in which sequence, thicknesses and material properties. So, design is nothing but selecting all these parameters. So, the design has to be selected in such a way that the computed strains will be less than the critical value or limiting value given by performance criteria or design criteria. There have to be some criteria which will tell us what will be the limiting values for a given situation for epsilon t and also epsilon z, so that the pavement can perform satisfactorily. So, we are coming to what is known as performance criteria. This is the heart of any pavement design procedure. So, once we have a design performance criteria, in this case we are talking about limiting strain criteria. There are two distresses that we are considering. For each distress there is a critical parameter identified. So, for a given situation, what is the maximum permissible value that this parameter can take, epsilon t and epsilon z, will be defined by the performance criteria. The limiting strains correspond to the initial condition of the pavement. This is very important, because the design that we select, layer thicknesses, material properties, all these correspond to the initial condition of the pavement immediately after it is constructed. So, the properties that are selected have to correspond to that condition. So, the strains also correspond to the initial condition. So, when a newly constructed pavement is analyzed and these two parameters are computed, if these two values satisfy the performance criteria, then the pavement is going to serve for a number of repetitions or 10 years or 15 years, whatever is the design life period. The analysis is done for initial condition of the pavement. The limiting strains will be smaller for higher traffic volumes. Obviously, if we want the pavement to be lasting for more number of repetitions, more years, obviously the limiting strain values will be smaller and smaller. So, as a result, we will have to be providing stronger materials, thicker pavements if the traffic volumes are higher or for longer design life periods. Indian Roads Congress adopts linear elastic layer theory for analysis of flexural pavements. In lesson 11, we have discussed about analysis of flexural pavements. We also discussed about the basis for selection of linear elastic layer theory, justification for linear elastic layer theory for analyzing flexural pavements, especially for highway traffic. So, IRC 37 guidelines consider linear elastic layer theory for analysis of flexural pavements. IRC also recommends that the pavements be modeled as typically 3-layer pavement systems. Although we know the pavements can have more than 3 layers, it can have sub base, it can have base, bituminous layers itself there can be more than 1 layer. So, it can be n layer system, 4, 5, 6 layers also can be considered, but IRC suggests that the pavement has to be analyzed as a 3-layer system: subgrade, granular base and bituminous layer. The interfaces between the layers, that is bituminous surface and granular base and the subgrades, are considered to be rough interfaces. We can analyze these pavements as smooth interface or as having rough interface also, but IRC considers the analysis to be having rough interfaces. The top 2 layers are assumed to be infinite in horizontal direction. These are the assumptions that we made in the case of analysis of flexural pavements using Burmister's layered analysis. The top layers are infinite in horizontal extent, having finite thickness. The bottommost layer is semi-infinite, infinite in vertical direction, in the bottom direction, downward direction, and this is a typical 3-layer system as per the model assumed in IRC 37. So, the inputs that we require, we have layer 1, 2 and 3. So, the inputs that are required are thickness of the first two layers H1 and H2 for analysis of this pavement. We need elastic moduli value of the 3 layers E1, E2, E3. We need Poisson ratio values of the 3 layers mu1, mu2, mu3. So, once we have this complete information, we can analyze this pavement for a given loading system. All these pavements for the purpose of design are analyzed for a standard loading condition. The standard loading being a standard axle load. We discussed about standard axle load in the previous lessons when we discussed about traffic considerations. Standard axle load is a 80 kilonewton load distributed over 2 dual wheel sets on either side of the axle and with a tire pressure of 0.56 MPa, that is about 80 psi. But for analysis we consider only one dual wheel system, because the other dual wheel system is at such distance, it will not have any significant effect in the parameters that we are calculating at these locations. So, normally instead of considering the total 80 kilonewton axle load, we consider only one set of dual wheel set and ignoring the other set that is there at the other end of the axle. So, when you consider half of the axle load, we have 40 kilonewton distributed over 2 wheels, this is the dual wheel set, 20 kilonewton, 20 kilonewton, tire pressure of 0.56, and typically it is seen that the center to center distance between these two dual wheel loads will be about 310 millimeters. This is what has been observed on several measurements that have been made on typical commercial vehicles that are plying in India. So, in this system what we are going to have is, for analysis, standard loading is 20 kilonewton on each load, 0.56 MPa tire pressure and center to center spacing of 310 millimeters. And for computation of these strains, the loads are considered to be circular in contact area. The vertical pressure, contact pressure, is considered to be uniform over the entire contact area, and no horizontal surface stresses are considered. We know that there can be horizontal stresses on the surface, but we consider only the vertical stresses for this analysis. Horizontal stresses can be there because of braking, acceleration, and also there will be centripetal inward stresses. The performance criteria adopted in IRC 37/2001 correlate performance with the critical parameters that were selected. There are two distresses that were interested in, and there are two mechanistic parameters that were selected to explain the behavior of pavement in terms of these two distresses, fatigue cracking and then rutting. We recollect that the two strain parameters, mechanistic parameters that were selected are tensile strain at the bottom of bituminous layer and vertical strain on top of subgrade. Performance is nothing but the number of equivalent repetitions of standard axle load that can be solved by the pavement before excessive rutting or fatigue cracking develop. So, performance is explained in terms of number of repetitions that the pavement can serve satisfactorily without excessive rutting or fatigue cracking developing. The general form of performance criterion is given as N is the number of repetitions that will be solved by the pavement satisfactorily as a function of initial strain. This may be initial tensile strain in the bituminous bound layer or initial vertical strain on top of subgrade. So, this is inversely related as per this general relationship. So, what we need to have is the correlation coefficient constants K1 and K2. The criteria developed by Indian Institute of Technology Kharagpur were adopted in Indian Roads Congress as performance criteria for both fatigue failure and also for rutting failure. These criteria were developed on the basis of vast data collected by IIT Kharagpur and several other institutions in India on the basis of performance data, observational performance data of several payments having different types of construction. All this data was pooled, analyzed, and two main performance criteria were developed. And the data was collected about the performance of payments under different loading and climatic conditions. In fact, the data was collected as part of different research schemes sponsored by Ministry of Road Transport and Highways, R6 and R81. These are the codes given by Ministry of Road Transport for these two main research projects. The rating criterion that has been adopted is NR is equal to 4.1656 into 10 to the power minus 8 into 1 by epsilon z to the power 4.5337, where NR is the cumulative standard axle load repetitions before the pavement develops 20 millimeter average rut depth. Epsilon z is the initial vertical strain on top of subgrade. So, we are referring to the initial vertical strain. This is computed corresponding to the initial condition of the pavement soon after it is constructed, when it is subject to the standard loading that we just discussed. If the pavement, for example, if the pavement has to serve about 50 million standard axle load repetitions without developing excessive rutting, that means without developing more than an average of 20 millimeter rutting. So, the initial vertical strain must be limited to, by substituting 50 million standard axles in the above equation, we get the corresponding epsilon z value to be 4.7201 into 10 to the power of minus 4. So, the initial computed strain should not be more than this value. So, the initial thicknesses, initial materials, because standard loading is already fixed, we are considering the standard loading, there is nothing to change there. Only thing that we can change is the layer thicknesses and the materials that we use. So, these have to be carefully selected so that the initial computed strain is going to be less than 4.7201 into 10 to the power minus 4 if we want the pavement to be serving at least 50 million standard axles during its service life period. Similarly, fatigue criteria, NF is given as 2.21 into 10 to the power minus 4 into 1 by epsilon t to the power 3.89 into 1 by epsilon modulus value of asphalt concrete to the power 0.854, where NF is the cumulative standard axle load repetitions before the pavement develops 20% fatigue cracking, and epsilon t is the initial horizontal tensile strain at the bottom of bituminous layer, because we already identified epsilon t is the parameter that explains the fatigue behavior. But another parameter is also added, which is the modulus value of the bituminous layer that we are going to use, because for different climatic conditions, if the pavement temperature is different, the modulus value will be different. Accordingly, the pavement performance is also going to be different. To account for that, the modulus value of bituminous layer is also brought into the equation. So, basically, to estimate how many repetitions a given pavement can serve satisfactorily, we have to calculate what will be the epsilon t, and we should also know what is the modulus value of bituminous layer for a given condition. For example, for a pavement to serve 50 million standard axle load repetitions without developing excessive fatigue cracking, that is more than 20% of paved area in a cracked condition, and if the modulus value of the bituminous layer is about 1000 MPa, then the initial tensile strain must be limited to 2.6453 into 10 to the power of minus 4. The pavement layer thicknesses and materials must be selected in such a way that both the computed strains will be less than the corresponding limited strains, is what we have been discussing. We have to select layer thicknesses and materials in such a way that the initial computed strains, when this pavement is subject to a standard loading condition, will be less than the limiting strains given by the performance criteria for a given traffic loading condition. This will ensure that the pavement will not develop unacceptable levels of fatigue cracking and rutting. Obviously, for an analysis of a selected trial pavement design, we need to be able to select appropriate material properties, because linear elastic layer theory is used for analysis. Elastic modulus value and Poisson ratio value of the 3 layers, because we are modeling the pavement as a 3-layer system as per IRC. So, these values are required for the 3 layers. Also, we need to be selecting, of course, in the trial thicknesses, we have to be selecting different thicknesses for the 2 layers. As far as the selection of subgrade modulus is concerned, the elastic modulus of subgrade can be determined by conducting repeated triaxial test on representative soil sample. We had discussed about determination of elastic modulus value of different types of materials in the lesson on material characterization. So, we can conduct repeated triaxial test on soil samples collected from field and then remolded on this specification. We can conduct repeated triaxial test under appropriate conditions. We can obtain resident modulus value or elastic modulus value for the soil, but usually it is difficult. Most agencies do not have this repeated triaxial test facility. So, normally this value is estimated from California bearing ratio value of the soil. Again, the soil has to be collected, so that representative soil has to be used and it has to be tested under standard conditions in the laboratory. That CBR value can be used to estimate residual modulus value of the soil. The expressions that are commonly used to estimate elastic modulus value or residual modulus value of subgrade soil is elastic modulus value expressed in megapascals is 10 times CBR for CBR values less than 5%. For stronger subgrades represented by CBR values greater than or equal to 5%, elastic modulus value can be expressed as 17.6 multiplied by CBR to the power 0.64, where E is the elastic modulus value of subgrade and CBR is the California bearing ratio of subgrade soil. For example, for a CBR of 4%, modulus value will be 10 into 4, that is 40 MPa, and for a CBR of 7%, modulus value of subgrade will be 17.6 into 7 to the power 0.64, that will be 64.8 MPa. Similarly, the granular layer material modulus value also has to be determined by conducting repeated triaxial test on granular material, but in the absence of equipment to conduct this test, this also can be estimated from the strength of the subgrade, which is represented by the modulus value of the subgrade, and also from the thickness of the granular layer that we are proposing to use. So, in the trial thickness, if we are proposing to use 300 mm thickness, we are checking whether this design is okay or not. So, our proposal is to use 300 millimeters of granular layer. So, for that thickness and for a given subgrade strength, which we already estimated from CBR value, or we have determined already by conducting a triaxial test. So, if you know the subgrade modulus value and also if you know what is the thickness of granular layer that we are going to propose, using these 2 parameters, we can estimate the modulus value of the granular layer using what is known as a shell equation, given as E granular base is a function of E of subgrade and then thickness of granular base, which is in millimeters. So, for a 300 millimeter thick granular layer placed over a subgrade having 40 MPa modulus value, the granular layer modulus value can be estimated as 104.2 MPa. Similarly, the elastic modulus value of bituminous layer can be determined in laboratory. We use different types of mixes for bituminous layers in India: bituminous concrete, semi-dense bituminous concrete, dense bituminous concrete, bituminous macadam. Typically, these are the materials for which elastic modulus values have been given in Indian Roads Congress IRC 37. And also mixes are typically prepared using different types of binders: 30-40, 60-70, 80-100 penetration grade binders, and also nowadays we use different types of modified binders: polymer modified binder, crumb rubber modified binder, and there are various other types of modified binders available. Normally we do not use 30-40 binder. 60-70 binder is the most commonly used binder nowadays, but however IRC gives modulus values for different types of mixes and prepared using different types of binders, not for modified binders of course. And we know that the modulus value of bituminous layer, bituminous mix is going to be different for different temperatures. So pavement temperature is an important parameter in selecting the modulus value of bituminous layers. 35 degrees centigrade is considered to be the average annual pavement temperature for most parts of India. We are talking about average pavement temperature, and this is the temperature, average temperature at which the mix is going to be for most part of its service life. So we are going to select a modulus value corresponding to 35 degrees pavement temperature. Research carried out at IIT Kharagpur and other places in India yielded typical elastic modulus values that can be selected for different average pavement temperatures applicable for different parts of India. Here representative values or typical values as recommended by Indian Roads Congress IRC 37 are given here for different types of mixes: bituminous concrete or dense bituminous macadam or bituminous macadam. There are three types of mixes that are considered here for different types of binders: 80-100, 60-70. This also should have been 60-70. Sorry, this is in fact 30-40, and then for BM 80-100 and for BM 60-70 also. So for some of these combinations modulus values are available, and they are available for different values of temperature. These are pavement temperatures, average annual pavement temperatures. So for typical or standard temperature of 35 degrees that we are considering for India, a modulus value of 975 can be considered if 80-100 bitumen is used. For same temperature, if 60-70 bitumen is used, a value of 1700 MPa can be used. These are all in MPa. And this value increases to 1945 or 1950 if 30-40 binder is used. Normally part of the dBm that comes out as the requirement in on the basis of the analysis and on the basis of the design that we do, part of this can be substituted by bituminous macadam, or one material can be substituted in terms of another material using the equal flexural stiffness principle. This is also recommended in IRC 37. The equal flexural stiffness principle is given as E1 H1 cube divided by 12 into 1 minus mu square. Basically we are trying to equate EH cube by 12 into 1 minus mu square of the two materials. So if you know the thickness of H1, the corresponding thickness of H2 can be obtained provided we know E1, E2, mu1 and mu2. Considering modulus values of 700 and 1700 MPa for bituminous macadam and dBm respectively, this yields the equivalent flexural stiffness principle yields 1 millimeter of dBm will be approximately equivalent to 1.34 millimeter of Bm. That means 1 dBm is equal to 1.34 Bm. Similarly, we can equate dBm to any other material if we have the properties of that material available for the same temperature. Poisson ratio values are the other important inputs that we require for analysis for analyzing the pavement system using linear elastic layer theory. The Poisson ratio value for bituminous mix for high temperatures such as 35 and 40 degree centigrade is taken as 0.5. For temperatures from 20 to 30 degree centigrade, the value recommended is 0.35. For granular layer and subgrade, a value of 0.4 is recommended. The general design approach includes selecting different inputs such as climatic conditions in terms of especially the average pavement temperature, whether it is 20 degrees, 25, 30, 40, and the general condition in terms of the rainfall, whether it is excessive, dry. These conditions will influence in selecting appropriate type of surface material, the number of layers that we are going to propose in the pavement system, the materials that we are proposing to use in each layer, the binder we are proposing to use, and the design subgrade CBR, the material has to be tested and this value has to be obtained, and the design traffic in terms of cumulative standard axle load repetitions. So, the design approach follows the next step being select trial designs and evaluate them. We can select various alternative designs in terms of various combinations of materials and also various combinations of thicknesses, and we can evaluate each one of them and see whether they satisfy the performance criteria. We remember that there are two criteria available, one for fatigue failure and the other for rutting failure. So, we select trial thicknesses for different pavement layers, having selected already the type of material that we are going to use, and we can also assign appropriate material properties to those materials. So, we have already selected the materials to be used. The only thing that is to be selected is the thickness of each layer. Assign appropriate elastic moduli and Poisson ratio values for each layer. We already have the guidelines for assigning them. Then compute critical responses. These are tensile strain at the bottom of bituminous layer and vertical strain on top of subgrade using elastic layer theory. That is what is indicated in the next point. Use linear elastic layer theory and considering standard loading conditions. So, this is how we analyze the selected pavement or trial design. We have selected H1 and H2. We also selected the material properties on the basis of guidelines that are available, and this is the standard loading that we are considering 20 kilonewton, 20 kilonewton at a spacing of center to center spacing of 310 millimeters, applied at a contact pressure of 0.56. We are also assuming that these to be circular contact areas. So, for these loading conditions for this pavement system, we select a trial combination of H1 and H2, then we calculate epsilon T and epsilon Z, then we will compare these two values with allowable values. So, evaluating the trial thickness, next step that we do is compare the computed strains with allowable strains for rutting and fatigue considerations. Allowable strains will be estimated for the given design traffic 50 millions, 20 millions, 100 millions, depending on the traffic intensity that is going to be there, depending on the number of years we have selected as design life period and various other traffic related parameters. We can estimate how many cumulative standard axles are going to be there in a given time period for this particular road. So, using that value n, substituting that in the limiting strain equations, we can get what are the allowable strain values. So, both allowable strain criteria should be satisfied. We are not going to be satisfied just either rutting criterion or fatigue criterion, both criteria have to be satisfied. If the criteria are not satisfied, we will select a new thickness combination and reanalyze. For the convenience of common user, design charts have been developed and they are also presented in the Indian Roads Congress guidelines. Using these charts, rather there are separate thickness charts are available for 1 to 10 million standard axles. This is a relatively low traffic volume, and for 10 to 150 million standard axles, these are relatively high traffic volume levels. These charts are available for subgrade values, CBR values of 2% to 10%, Also these charts are available for dense bituminous macadam prepared with 60-70 bitumen. This is considered to be the bituminous layer. This is the limitation of these charts. Only we can get dense bituminous macadam thickness using these charts. These are available for 2 to 10% CBR values. Also these are available for 1 to 150 million standard axle repetitions. What the chart gives us will be the total thickness for a given CBR value and for a given traffic level if design charts are used. Of course, if you are using a computer program using which you are capable of analyzing pavements, computing strains, so there is no limitation of us getting total thickness. We can select different combinations of thicknesses and check whether they are appropriate or not. But if you are using design charts given by in IRC 37, what we get is the total thickness. Obviously that has to be split into different component layers. There are two thicknesses that we have to split this total thickness into: thickness of granular base. In fact, it has to be split into thickness of granular subbase, thickness of granular base, and also thickness of surfacing. So these are the three components into which we have to split the total thickness into granular subbase, granular base, and bituminous surfacing. This is how a typical thickness chart looks like. This is what is given in IRC 37, although I have not put the values here. So for a given traffic volume which can be estimated for a given design period, and for a given subgrade CBR value, the total thickness to be selected is given by the chart. Once we obtain this total thickness, this is the total pavement thickness. This can be split into the component thicknesses. So the cumulative number of standard axle load coverages expected during design life period can be estimated from this. We have briefly discussed in an earlier lesson which was exclusively dealing with traffic related parameters. We have to know the initial traffic intensity after construction in terms of commercial vehicles per day. We also should have the traffic growth rate during the design life period. We should know the design life in terms of years. We should have some knowledge of the vehicle damage factor that is likely to be there, VDF. We also have to have some lateral distribution factors to account for the lateral distribution of commercial vehicles across the carriageway. So these are the parameters that should be able to select. IRC gives guidelines for selecting all these parameters. Design life typically has to be selected as 15 years for high volume roads, national highways and state highways, 20 years for expressways and urban roads. For other categories, it can be 10 to 15 years. In selecting this design life period, we should also take into consideration the possibility of constructing the pavement in different stages, stage 1 and stage 2. The vehicle damage factor, this we have discussed earlier in the earlier lessons, is a multiplier to convert the number of commercial vehicles of different axle loads and axle configurations into equivalent number of standard axle load repetitions. VDF can be obtained from axle load survey. In the absence of any axle load data, if you are not able to conduct an axle load survey, the following values can be adopted. These are the values that are recommended by Indian Roads Congress. For an initial traffic value of 0 to 150 commercial vehicles per day, CVPD is commercial vehicles per day. For different terrains, rolling and plain terrain, hilly terrain, the values recommended are given. For example, for rolling and plain terrain, for initial traffic intensity of commercial vehicles of more than 1500 commercial vehicles per day, a value of 4.5 can be selected if it is in a rolling or plain terrain. Similarly, for lateral distribution, for single lane road, 100% of the total two-way volume has to be considered. For two-lane road, single carriageway, 75% of total two-way traffic has to be considered. For four-lane single carriageway, 40% of total two-way traffic has to be considered. For dual carriageway roads, for dual two-lane carriageway, 75% of traffic in each direction. For dual three-lane carriageway, 60% of traffic in each direction. For dual four-lane carriageway, 45% of traffic in each direction. If we do not have directional distribution of traffic, we can assume that traffic in each direction is half the total traffic. Okay. An annual average growth rate of commercial traffic can be assumed to be 7.5% if no projections are available. So, estimation of design traffic can be made using this expression where n equal to 365 into A is the commercial traffic volume intensity, commercial vehicles per day, D is the directional distribution factor. We will see the explanation of these parameters in the next slide. D is the the lane distribution factor, F is the vehicle damage factor, N is the design life in years, R is the annual rate of growth of commercial vehicles assumed to be 7.5% in the absence of any data. The traffic in the year of completion of construction, that is A, can be estimated if you know what is the present traffic intensity at the last count, and also number of years between the last count and year of construction, that is X, using this expression. The pavement composition can be selected if you know the total pavement thickness using this catalog or tables that are given in IRC 37. So, for different subgrade CBR values and for different traffic intensities, for the total thickness how it has to be split for different traffic intensities of 1, 2, 3, 4, 5 and 10 million strand axles, this is how the total thickness has to be split. Similar tables are available for traffic intensities for 10 to 150 for different subgrade CBR values. So, you will have a number of tables available in IRC 37 for different traffic intensities, different subgrade values and for different types of materials. The pavement composition that has to be used typically should be subgrade should have a minimum CBR of 20% for traffic up to 2 million strand axles. It should have a minimum 30% CBR for traffic greater than 2 million strand axles. For subgrade CBR soils of low permeability, the granular surface should be for full width of formation. The thickness of the extended portion should not be less than 150 millimeters for traffic less than 10 million strand axles and 200 millimeters for traffic more than 10 million strand axles. If the subgrade CBR is less than 2%, design of CBR of 2%, the design should be for CBR of 2% and provide a capping layer of 150 millimeters thick material having minimum 10% CBR in addition to the sub base. Base should be minimum thickness of 225 millimeters for traffic up to 2 million strand axles, 250 millimeter for traffic more than 2 million strand axles. Material should conform to MORTH and then IRC specifications. Bitumen surfacing can be a combination of wearing course or wearing course plus binder course. Wearing courses typically are surface dressing, open graded premix carpet, mixed seal surfacing, semi dense bituminous concrete and bituminous concrete. Binder course can be bituminous macadam and dense bituminous macadam. Use of bitumen typically having low bitumen content, high air voids to be restricted for traffic less than 5 million strand axles. We should normally provide dBm for traffic more than 5 million strand axles. Equivalence of Bm in terms of dBm is approximately 10 Bm is equal to 7 dBm. Selection of binder type and mix type to be made on the basis of traffic and climatic conditions. For snowbound areas, bus stops, roundabouts, provide bituminous concrete for waterproof, stable surface. Mastic asphalt also can be used. Open graded premix carpet of thickness up to 25 millimeter thickness is not considered as a structural layer. IRC 37, the main limitations are thickness charts are still available compared to the previous version, still available for only CBR up to 10%. Design charts are available for only pavement temperature of 35 degrees centigrade. Charts are there for only for dBm bitumen surfacing only. The contribution of individual component layers is still not realized fully with the system of catalog or block thicknesses. What the chart gives you is only the total thickness, how this has to be split into different component layers. If more surfaces is provided or more base thickness is provided, what will be the effect on the performance cannot be explained using these charts. Of course, the same can be done through the use of an analytical tool for design instead of resorting to thickness charts. To summarize, in this lesson we have learnt the basis for IRC method of design for flexible pavements. We also understood about the performance criteria adapted in these guidelines. We have learnt about the model used in the guidelines for analysis of payments, and we also understood how different traffic and material related parameters are to be selected for designing the payments, and we have also understood the limitations of the method of IRC 37/2001 method of designing flexible payments. Let us take a few questions from this lesson. Answers for these questions will be provided in the next lesson. What are the main modes of failures considered in IRC 37/2001? What are the mechanistic responses considered in the design process to account for the failure modes? What is the standard loading configuration to be considered for analysis of payments? What is the recommended approach for selection of granular based modulus? What are the main limitations of IRC 37/2001? Now let us see the answers for questions that were asked in lesson 4.12. What is the main difference between flexible payments and rigid payments? Compared to flexible payments, rigid payment has got a very stiff slab. The deflection is negligible compared to the deflections that flexible payments undergo. This is the main difference. As a result, the stiffness of the slab is predominant in terms of explaining the performance of the payments compared to flexible payments. So the foundation strength in the case of rigid payment is not so important as it is in the case of flexible payments. Next question is, what is the function of contraction and expansion joints in concrete pavement? If you construct a very long slab without any joints, it is anyway going to crack because of contraction. As the temperature decreases, slab is going to contract. So there is going to be some restraint that is going to be available to be provided by the foundation. So as a result, there are going to be tensile stresses developing. It is going to crack. To regulate the location at which the cracks are going to be forming, we are going to weaken the slab at regular intervals and thereby allowing the crack to develop at that location only. So that's the reason we have to provide contraction joints. Whereas expansion joint is to allow for the expansion of the slabs, because slab is going to expand when the temperature increases, but there has to be some gap that is available between different slabs to accommodate that increase in length of the slab. So that's the reason why we provide expansion joints. What is the function of dowel bars and tie bars? Dowel bars are provided to provide load transfer mechanism from one slab to another slab. They are meant for load transfer from one slab to another slab, either across a contraction joint or across a expansion joint. On the other hand, tie bars are there to tie the two slabs together, see that the gap does not open, and thereby the load transfer mechanism is there through granular interlocking. What is the most commonly used parameter to characterize foundation for analysis of concrete pavements? It is modulus of subgrade reaction, and this can be obtained by conducting a plate load test by applying load incrementally and then observing the deflections, and the load corresponding to deflection of 1.25 millimeter can be observed. So the unit pressure corresponding 1.25 millimeter pressure divided by 1.25, that is the value of K. This can be obtained by conducting plate load test. Why do thermal stresses occur in concrete pavement? Thermal stresses typically occur, especially we are talking about curling stresses, when the top temperature and bottom temperature of the slab differ. If the top temperature is more, the slab will curl like this. If it is restrained from curling up like this because of its self weight or because of the restraint provided with the foundation, there are going to be stresses developing. Similarly, if the bottom temperature is more than the top temperature, it will curl up like this. So because of the self weight it is restrained, or the foundation also will restrain it. Because of the restraint, curling stresses are developed.